Hi all. So today we are going to discuss about parallel processing and pipelining as part of Computer Organization and Architecture Unit 4. So now first let us talk about parallel processing. Parallel processing, it is a class of techniques which enables the system to achieve simultaneous data processing to increase the computational speed. So here sequentially when we are executing some instructions, it will take more time. So to increase the speed, what we are doing, we are simultaneous data processing tasks we will perform. That concept we call it as parallel processing. So here for instance, if we are taking when an instruction is being processed in a ALU component of CPU and next instruction can be read from the memory, because these two are the independent instructions. They are not dependent on each other. Parallelly also they can be performed. So such type of instructions, if parallelly if we are executing, then we can speed up the execution time. So for that reason we are using this parallel processing system. So here the main purpose why we are using this parallel processing, if we are taking, the primary purpose of parallel processing is to enhance the computer processing capability and increase the throughput. That means the amount of processing that can be accomplished during the given interval of time, that can be increased. So now how this is done? So this is done mainly by having the multiplicity of functional units. Various functional units we will have which are independent, that means parallelly which can be performed. So these various functional units, if we are taking, how it is possible, how we can do that? One of the ways, one of the possible way, if we are taking, we will separate the executive unit and 8 functional units. So generally we are having 8 functional units. So basing on the functionality, what functions we are performing and what functions we can perform individually, that we are separating. We are maintaining the functional units and executive units separately we are having, the processor separately we are having. Let us see the block diagram. So the block diagram, if you observe, here you can observe that the processor within which we are having the registers where the execution part is done, the memory to and from the connection with the processor we are having, and along with these are the 8 separate functional units which we are maintaining, and they are in both the ways they are connected to the processor. So these 8 functional units, if we are taking, first one, adder subtractor, which is used for the addition and subtraction performing, integer multiply, which is used for the multiplication purpose of the integers, logical unit, we are having the shift unit which is used to shift the bit, right shift, left shift, various shift registers, shifting the data or bits in the register, we will use the shift unit. Incrementer, which is used for the incrementing purpose, one value it is incremented. Floating point addition and subtraction, separate unit we can maintain. Floating point multiplication, separate unit we can maintain, and floating point divide, separate unit. All these units individually, they are not dependent on each other, and parallelly they can perform the operations. So here if you are checking that the same block diagram, it is explained here. Adder and integer multiplier, if you are taking, for example. So you can perform the arithmetic operation on integers and multiplication of another set of integers parallelly. They are not dependent. The same way floating point operations, they are separated, and logic shift increment, if you are taking on different data, if you want to perform, you need not to wait that one after other sequentially only they can perform, they can also be performed parallelly. So like that way they are independent. First thing is, all these units are independent of each other. They are not dependent. Dependent in the sense, one unit after performing the output, whatever you are getting, that will be taken as the input of the other. It is not like that way. Individually all these units, they can be work and perform the operations. So here a multifunctional organization, actually it is associated with complex control unit. So this, it coordinates all the activities for overall various components, and it is maintaining this how it can be conducted. So here for this conduction mainly three ways are there, or three things you have to keep in mind. First one is internal organization of processes. So when we want to perform parallel programming, there we have to do the internal organization of the processor. So single system or single processor if you are taking, it is simplest, or there is no complexity at all. In a simple way the organization will be done. But multi-processing or parallel processing if you are doing, there particular internal organization according to how you are performing that processing parallelly, according to that internal organization is to be done. The same way interconnection structure between the processes. When we are talking about multi-processing, so multiple processors will be connected to perform various operations. So how that interconnection between the structure of the process, how you are maintaining, you have to concentrate on that. The same way the flow of information through the system, how the flow of information it is maintained, that is to be concentrated. These are the ways how the parallel processing it is to be done. Now classification of parallel processing if you are taking, there are various ways how we are classifying. Here we are talking about MJ Flame. So he introduced that mainly this processing, it is made up of two different things. One is instruction stream and second one is data stream. Instruction stream, it is nothing but the sequence of instructions read from the memory constitutes the instruction stream. So already we have studied in the previous units how the instruction is executed, or how this memory is maintained. We are maintaining the memory to store the data or store the words. Words if you are taking, then that word may be an instruction or that word may be a data. So here the instruction related word if you are taking, the how that instructions are read from the memory, that constitutes the instruction stream, and the operations performed on data by the processor, that constitutes the data stream. So basing on these two, whatever the classification you are talking about, it is divided into four different classifications, four different categories, we can say four different groups. So first one is single instruction stream, single data stream. So in this method we are having only one instruction, one processor and one memory. Single instruction and single data stream we are having. Second one, we are having single instruction stream, multiple data streams. That means one instruction stream only we are having, that means one instruction it is given to the processor, but it is distributed among various processes, and data parallelly it can be maintained, various streams of how you are accessing the data and working on data, it can be done in the multiple ways. Multiple instruction stream, single data stream, that means multiple instructions are given but the data only one stream you are maintaining, and multiple instruction stream, multiple data stream where both instruction streams also different ways you are maintaining and data streams also different ways you are maintaining. Let us see one by one. First one, single instruction stream, single data stream if you are taking. Here as I told you, it is the simplest way and simple or single computer here we are using. Here we are having, it is consisting of one control unit, one processor and one memory unit, all only single things you are having. So here what you are having, instructions are executed sequentially, one after other it is executed, and the system may or may not have internal parallel processing. So sometimes it may have and sometimes it may not have. Suppose if it is having internal parallel processing, then what is the way it is using? It may use either multiple functional units it may use, or pipelining processing it may use. These are the various ways when we are using single instruction stream, single data stream, how internally the parallel processing it is done, if at all it is using. So sometimes it may not use also. Here main thing you have to remember is single processor, single control unit and single memory unit you are having. So here single instruction stream you are having, it is given to the processor, and single data stream it is having, it is contacting with the single memory unit, and this is the simple diagram or schematic diagram which is used for the single instruction, single data stream. So here the instruction stream, you can observe, instruction stream, it is given to the instruction, then it is connected to the memory, and data stream, if you are taking, data stream mainly meant for the operands, how they are stored. So here data stream, operands are located, and that located operands, that memory address, it is given to the processor for the further execution. Second one, if you are taking single instruction stream, multiple data stream. So as I told you, single instruction stream means only one instruction it is given. So this instruction, it is splitted and multiple, it includes multiple processing units. So these multiple processing units, each and every processing unit, it is dealing with the multiple memory units. So here it is dealing with the memory each and every time. So multiple data streams we are having, but single instruction stream we are having, single instruction stream and multiple data streams. Next one, it is multiple instruction stream, single data stream. Actually it is possible or it is proved only theoretically, and practically the implementation is not possible. So here on theory we can see this, that there is multiple instruction and single data stream is there. Theoretically we can prove, but practically till now no system was implemented. So only theory part we can have for this. Next one, we are having multiple instruction stream, multiple data stream. So as the name suggests, multiple instruction streams we are having, multiple processors we are having, processing units, and each and every processing units, they are individually connected to the memory unit. So multiple data streams also we are having. So here completely 4 different types we are having: single instruction unit, single data stream, single instruction stream, multiple data streams, multiple data stream, multiple instruction stream and single data stream, and multiple instruction stream and multiple data stream. These are the 4 different ways how we are maintaining this. And this multiple instruction stream, multiple data stream, if you are taking, the latest used, most popularly used multi-processors, multi-computer systems, all these are classified into this category. Now let us see the parallel processing. What are the main topics that are covered in the parallel processing? So in parallel processing we are having pipeline processing, most popular pipeline processing, how it is done. Vector processing. So pipeline processing, if you are taking, here we are using the technique, the implementation technique, where arithmetic sub operations, one operation or one instruction if you are taking, that instruction it is divided into sub operations, and basing on the sub operations we are constructing the segments, and these segments step by step they are implemented in a pipelining system. And in most cases these sub operations which we are defining, one sub operation or one segment, we are giving the input to that segment, and the output of that segment, it will be acting as the input to the next segment. That is why we are calling it as pipeline processing. That in the next slides we will see about that. Next one, we are having the vector processing. So this vector processing, it deals with the computations involving large vectors and matrices. And third one, we are having the array processing. Here performing computations with large arrays of data, we are having the array processing. Here we are concentrating on this pipeline processing, how it works. So let us see about the pipeline processing and various ways or various types what we are having in the pipeline processing. Here we are having various types of pipeline processing: arithmetic pipeline, instruction pipelining, processor pipelining, unifunction versus multifunction pipelining, static versus dynamic pipelining, scalar versus vector pipelining. But here in our syllabus, in our unit, we are going to concentrate on arithmetic pipelining and instruction pipelining. Only these two things we are going to learn. Now let us see what do you mean by pipelining. Already I told you. Here pipelining, it is a technique that one process, whatever the process you are taking, that it divides that process into several sub operations. So when we are taking any instruction, when you are taking any operation, as it is, if you want to perform, it will be divided, it will be difficult. So what we will do, we will divide that into small parts. And parallelly, sometimes it is possible for us to do these parts parallelly, we can execute. So let us see. Finally, what we have to do, at the starting we are giving the instruction input to the instruction. Once everything is executed, last we are getting some output. So finally, the output of each segment, it is stored in the registers. Processor, when we are talking about intermediate data, it is stored in the registers. So this segment, it is storing in the register, and that, as I told you, one segment, the output of one segment, it will be acting as the input of the next segment. So here intermediate, for each and every segment, this output, it is stored in the register, and the same it will be passed to the second segment. Suppose if we are dividing one instruction into 3 segments. So first segment we are sending the input, it is executing, it is getting some output. That temporary output, whatever we are getting, we are storing in one register, and that register content we are sending as the input to the second segment. Second segment, when it is completing, again one output we are getting, that output in another register we are storing, and the content of that register again we are sending to the third segment. And finally, whatever the output we are getting, that in the final register we are having that output. So let us see an instruction pipelining. So an instruction in a process, any instruction if you are taking, basing on the task which it is performed, it is generally divided into 5 tasks. What are that 5 tasks? First one, fetching of the instruction, because already previous chapter we have studied about how an instruction is being executed. First step is fetching the instruction. Second step, once we are fetching the instruction, we have to decode that instruction. After decoding, in that instruction, whatever the operands are there, that operands we have to fetch. Next, we are having execution of the instruction. So once the execution is over, we are having the output. That output we have to store the operand where we are having the output. These are the 5 parts or 5 subtasks which are divided for a particular process. So the same thing it is given here. The first subtask, the instruction is fetched. Second one, the fetched instruction is decoded. Third one, the operands of the instructions are fetched, because suppose if you are taking A, C is equal to A plus B. C is equal to A plus B means A and B are the operands and plus is the operation. So first you are fetching the instruction, then decoding the instruction, then A and B are to be fetched, that you are fetching. Then fourth one is whatever the operation you have to perform, you are performing. So now you are having the value of A, now you are having the value of B, now you are performing A plus B, and the result is there, the result is stored in C. So that's C, the 5th stage, it is the result is stored in the memory. So here now while you are doing the processing in the registers, temporarily you will store the result, but finally in the memory you have to give some address where you have to store the result. These are the 5 stages or 5 subtasks how a process of executing an instruction it is divided into. Now let us see the same thing we are explaining here. Suppose you are having 5 instructions to be executed. Here T0, T1, T2, T3, these all are the time cycles. So at one cycle, one part or one subtask of one instruction it is executed. So here it is divided into clock cycles. Now instruction 1, we are starting with the instruction 1. For instruction 1, as I told you, each and every instruction it is divided into 5 subtasks. So, how many clock pulses are required to complete the execution of one cycle? First clock pulse, fetching of instruction. Second clock pulse, decoding the instruction. Third clock pulse, operand fetching. Fourth clock pulse, executing the instruction. Fifth clock pulse, storing the data of output onto the memory. These are the 5 subtasks which are to be performed when one particular instruction is to be executed. So, here instruction 1, it is started at the clock pulse T0 and 5 different cycles the instruction is completed. Second instruction, if you are taking, in the first clock pulse, only first instruction, first subtask it is performed. In the second clock pulse, first instruction, decoding of instruction is done. At the same time, second instructions, fetch instruction subtask also parallelly can be done, because fetching the instruction and decoding the instruction both are individual or independent events. They are not dependent on each other. Parallelly they can be performed. So, here in the first clock pulse T0, only first instruction fetching it is done. The remaining you are not having anything. In the second clock pulse, the first instruction, already fetched instruction, it is decoded, and also parallelly second instruction is fetched. Third clock pulse, already here fetched instruction is there. So, here we can decode the instruction. Here already decoded instruction is there. Here we can fetch the operands, and third instruction it can fetch the instruction. So, you can say that all the 5 instructions they can fetch the instruction. No, only one at a time they can be fetched. So, first one, only one it is done. Here 2 are done in the second clock pulse. Here 3 subtasks can be performed parallelly as they are independent, and in the fourth clock pulse 4 different events can be performed, and in the fifth clock pulse 5 different events which are related to 5 different instructions they are being executed. So, this is parallelly done. So, now to complete all the 5 instructions, how many clock pulses are required? Starting from T0, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9. Total 9 clock pulses are required to execute 5 instructions for each and every instructions when it is divided into 5 subtasks. Suppose you are not using parallel processing and sequential processing only you are maintaining, then for each and every instruction 5 subtasks are required and 5 clock pulses are required. So, that means after completing these 5 subtasks, here you are going to start the second instruction, again 5. After completing that, again third instruction. That means for each and every instruction 5 clock pulses. Total for completing 5 instructions execution you require 25 clock pulses, whereas by using this parallel processing it required only 9 clock pulses to complete the complete execution of all 5 instructions. That is the advantage of using parallel processing. So, now let us discuss the same thing using one example. So, here let us take one example, AI into BI plus CI for I is equal to 1, 2, 3, so on 7. This is the instruction set of instructions which are to be executed. Now, here by using pipelining organization how it can be done, and by using without using parallel processing if you are doing how it is done, let us discuss about that. How many variables are there for each and every instruction? 3 variables are there. How many operations are there? 2 operations are there. One is multiplication, second one is addition. And like that way, how many times we have to perform? for 7 different values we have to perform the same instruction or same operation it is to be performed. Now let us see what are the minimum number of subtasks we can divide or segments we will call that. So when we are dividing this, how many segments we can divide this. So first one if you are taking, the first thing is we are fetching the instruction. After fetching, here we are talking about only the execution part. So here 2 operands are there, A and B. So A and B we are reading, we are taking input A and B. After inputting A and B, where we are storing 2 registers are required to store the values of A and B. So we are reading A we are storing in R1 and B we are storing in R2, and that we are taking as one, considering as one segment. Then R1 into R2, what is our instruction? AI into BI plus CI. So the first part if you are taking, that is A into B. A into B means where we are having that contents in R1 and R2. So here we have to perform one multiplication operation. So R1 into R2, content of R1 into content of R2. In R1 we are having A1 value and in R2 we are having B1 value. Okay. Now we are multiplying these 2 values and storing in R3. Parallelly, the input of C, because next statement we are having, we have to add this content to C. So that is also to be stored into register. So C value we are reading and storing in R4. These 2 are independent statements. So parallelly they can be done. These instructions we are taking as segment 2. Now third segment, now this in R3 we are having the product of the values A and B. In R4 we are having the value of C. Now we want the value of sum of R3 and R4. We are adding these 2 and the addition, we are adding Ci to the product and the result we are storing in R5. This we are considering as segment 3. So the given instruction AI into BI plus CI, for 7 different values we have to perform that. For one value, this instruction it is divided into 3 different segments or different subtasks. Now total how many registers are required to complete the task? R1, R2, R3, R4 and R5. So total 5 registers are loaded with new data with every clock pulse. Now R1 and R2, in the first clock pulse we are taking A1 and B1. Simultaneously at the same clock pulse we cannot take again A2 and B2. Only in the next clock pulse we can do. But in the next clock pulse, A2, B2 we can store in R1 and R2 simultaneously. This R3, R4 also we can do. So some overlapping will be there. Let us see that in a tabular form. So here we can see this is the clock pulse numbers and these are various segments. As I told you, in segment 1 we are dealing with R1 and R2. In segment 2 we are dealing with R2 and R4, R3 and R4, and in segment 3 we are dealing with R5. So clock pulse 1 if you are taking, at a time you can do only once R1 and R2. So A1 is stored in R1, B1 is stored in R2, the remaining segments you are not touching in clock pulse 1. So first clock pulse only these operations, and that means segment 1 is performed, that is all. Segment 2 if you are taking, already we are having A1 and B1 in R1 and R2. So segment 2, what is the segment 2? R1 into R2. So this R1, A1 into B1, segment 2, it can be executed. Along with that, R4, the content of C1, it is stored in R4. That is also executed. And once it is executed, that means R1 and R2 are free. Now we can load new values. What are that new values? A2 and B2, these new values are added to, are loaded into R1 and R2. So in the second clock pulse, we are updating we are assigning A2 value in R1, B2 value in R2, and previous A1 and B1 already we are having. So, we are executing A1 into B1 and C1 value we are loading into the R4, and segment 3 we are not doing in the second clock pulse. In the third clock pulse, so first we will come here, already we are having A1 into B1, C1 value we are having. So, third segment we are having A1 into B1 plus C1, that is stored in R5. So, that is the third segment. Third segment we are executing. Simultaneously, this A2 and B2 are available in R1 and R2. So, A2 into B2, C2 is loaded into R4, that is also done, and in the same clock pulse, new values are assigned to R1 and R2, A3 and B3. So, from here at each and every step, next step we are assigning new values to R1 and R2, A4 and B4. We are multiplying this and assigning in R3. That means at each and every clock pulse, the data of that particular registers, they are being updated. So, by doing this, for implementing the instruction for 7 different values, how many cycles are required here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 clock pulses are sufficient to execute the instruction for 7 different values for I is equal to 1, 2, 3, 4, 5, 6, 7. Suppose if you are not using the pipelining, suppose if you are not using the parallel processing, directly you are using the sequential processing and performing the same operation, for executing one instruction, 3 segments are required. To execute 3 segments, 3 clock pulses are required. That means totally 7 different values for the instructions. For each instruction, 3 different segments, 3 clock pulses, 3 into 7, 21 clock pulses are required to complete this task individually if you are doing. By using the parallel processing, it was completed in only 9 clock pulses. That is the advantage of using the clock pulse. So, the same thing if you are representing in a diagrammatic manner, you can say that first segment, this is the first segment, that is A1 is assigned to R1, R1, R2, R3, R4, R5, these are the registers. Multiplier, adder, these are the operations which are performed. So, first segment you are assigning AI to A1 to R1, A2 to R2, or AI, BI if you are taking AI to R1 and BI to R2. In the second segment, you are multiplying these two and storing in R3. CI is assigned to R4, this is the segment 2. And in segment 3, you are adding the values of R3 and R4 and storing the result in adder, storing the result in R5. This is the execution of one instruction for one value. So, for I is equal to 1, the complete cycle is required. I is equal to 2, complete cycle is required. Like that way, for 7 different values, 7 different cycles are required, and for each cycle 3 segments are required. So, total 21 segments are required if individually it is done. By using parallel processing, by using pipelining processing, it is completed with only 9 cycles. So, here you can say the same thing, it is explained here. So, A1 into B1 plus C1, 3 segments, it is divided into 3 segments, that means 3 clock pulses. Value 2 for I, again 3 clock pulses. The same way continuously, value 7 for I, 3 clock pulses. Total 1, 2, 3, 4, 5, 6, 7, 7 into 3, 21 clock pulses are required to complete the task if it is done individually or sequentially. By using this pipelining process, by using this parallel processing, we are going to complete this in only 9 clock pulses. That is the advantage of using the pipeline.